This time we're thinking about equilibrium. Equilibrium means no accelerations of any kind, no meters per second accelerations, and if that's the case, then the net force on the object would be zero, and it also means no angular accelerations, which means that the net torque must be zero. And those two ideas right there are the basis of all of our problem solving in any equilibrium situation. So here's a first example, but just a reminder how you find the magnitude of a torque. It's just force times the magnitude of a displacement vector and sine of an angle. And the sine is determined by what kind of rotation that torque would produce. If it makes a counterclockwise rotation appear, we'll have these backwards, that corresponds to a positive torque, and if it made a clockwise rotation appear, that would correspond to a negative torque, and you have to get those signs right when you're combining torques, adding them together to get the net. So imagine this situation. We've got a beam attached at one end to a wall, and then it's held up at the other end by a cable, and this might be the awning in front of some building, and you might put a sign in front of that awning. But all we have in this case is just the beam being held up by the cable. The mass of the beam is 40 kilograms, and the beam is 3 meters long, and we want to figure out how strong the tension force has to be in that cable in order to keep holding up the beam. Or to put it another way, how strong does the tension have to be to keep the beam in equilibrium, to keep it in a state where the net force remains zero and the net torque remains zero. It doesn't start to accelerate at all. Right, the most likely way in which it would start to accelerate is if the tension is too weak. Then this beam would start rotating this way. In other words, the rotational velocity of the beam would change from zero to not zero. Change in the rotational velocity, also known as angular velocity, means there's angular acceleration, which would be caused by a net torque. But as long as it maintains the same state, there must be zero net torque and zero net force. So the way we start this question, what we're looking for is figure out how strong that tension force. The way we start is the way we always start. What forces are acting on the thing, and what directions are those forces pointing? Now we have to add one extra little wrinkle. We're looking at an extended object, not just an object that we could model as a point of mass. So we also must be careful to specify where on the object that force is acting. So our force diagram would look like this. There's the tension on the far end pulling this way, and then there's weight. And remember, when we're thinking about the weight force on an object that's extended, an object that has volume, an object that isn't just a point, we think of that weight force as acting only on the center of gravity. And if the mass is evenly distributed throughout the whole length of the object, the center of gravity is right in the middle. Right? You can think of the center of gravity as sort of the average location of mass. And if there's mass evenly spread out, then the average location will just be right in the middle. So the center of gravity is right there, and that's where the weight force pulls on the beam. Okay, that's two forces, and we know there must be one more force. There must be a force from the wall on the beam. We don't know much about that force from the wall on the beam. The one thing we do know is that that force on the wall, from the wall on the beam, has to have a rightward component, because the net force on the beam is 0, and this tension force has a leftward component. It has some leftward pull as well as some vertical pull. And in order to keep the net force 0, this leftward pull from the tension has to be canceled out by some rightward push from the force from the wall. So some kind of force from the wall on the beam. We don't, strictly speaking, we don't know the direction of that force. All we know is that it has to have a rightward component. So it could be a force pointing in that direction, or it could be perfectly horizontal, or it could be pointing in a direction like that. Now, the next step, figure out what the torques are. Each force could cause a torque. Figure out what we know about that torque. We might be able to calculate a number, or we might be able to just write down some algebraic expression for that torque. Just the appropriate version of this for that particular force. But before we can calculate a torque, we need a reference point. The good reference points are usually at axes of rotation, and if there were rotation, it would be a rotation about an axis that passes through here, so this makes sense to put the reference point right there, right at the wall. Another reason to put the reference point right here is that whatever force is acting at the reference point, that produces 0 torque, because this factor in the force equation is just the magnitude of a displacement from the reference point to the force. But here, the reference point is right at the same point where the force is acting. So the distance between the reference point and the point where the force is acting is 0, so that force produces 0 torque. That's good, because we don't know anything about this force, and if this force produced a non-zero torque, we would have this unknown in all of our equations. We've already got one unknown, this. If we have 2 unknowns, that makes the problem a lot harder. A lot harder than it needs to be, because we can just put the reference point right here, making the torque due to the wall force 0, and when we do that, we don't have to worry about that force at all any longer. So, what are the torques like? Torque from the force from the wall on the beam is, like I just said, 0. Now, torque from the weight. We're able to get a number for that one. The mass of the beam is 40 kilograms, so the weight force of the beam is mass times g, 40 kilograms times g, 40 kilograms times 9.8, and that gives us 392 newtons. Right, that's just the mass of the beam times g. So the magnitude of the force, that's the first factor in the torque. Then magnitude of the displacement. Displacement takes you from the reference point to the point where the force is applied. So this reference, this displacement starts here and ends here. The size of that displacement is half the length of the of the beam, so half of 1.3 or 1.5 meters. And then the third factor is sine of the angle. That angle is always the direction between the displacement direction and the force direction. Remember, the displacement goes from the reference point to the force, so the direction of displacement is horizontal to the right, and this force is down, so the angle between displacement direction and force direction is 90 degrees. Sine of 90 degrees is just plain 1. So that's the magnitude of the torque, 392 newtons times 1.5 meters. We need to pay attention to the sign. And in order to get the correct sign for that torque, we ask what kind of rotation would it produce? Well, a pull right here at the middle of the beam would make the beam rotate this way. If we're taking that as our axis of rotation, it would make the beam rotate clockwise, and any torque that would make a clockwise rotation happen we call a negative torque. So this is going to be a negative number. That. Okay. So then torque due to the weight is minus 392 newtons times 1.5 meters, or minus 588 newtons times meters. Now last torque, the torque due to the tension, we cannot get a number for that because we don't know the tension. Tension is the thing that we're trying to find. So all we can do is write an algebraic expression. An algebraic expression just means one of the factors in there is an algebraic variable. Okay. So that is magnitude of the force, and all we can do is call that T, times magnitude of the displacement vector. In this case, the displacement vector takes us from here, the reference point, to there, where the force is acting. The size of that displacement vector is therefore the whole length of the beam. So 3 meters. And then the sine of that angle, the angle is the angle between the displacement direction. The displacement starts here and goes to here, so the displacement is horizontal to the right, and then here's the force in this direction. So the angle between displacement direction and force direction is all that angle. And from here to here, of course, is 180 degrees. So the angle between displacement and force is 180 minus 30, 150. Sine of 150 degrees. Okay, so now let's answer the question. Let's actually figure out what that tension is. To do that, we need an equation that involves T, and then we solve the equation for T. Well, the equation that will include T is this. That net force, which is 0 because we're in equilibrium, is just the sum of the 3 torques. 0 is the torque from the force from the wall, and then minus 588 newton meters is the torque from the weight force, and then plus T 3 meters sine 150. Sine of 150 turns out to be half, So this is T 3 meters times 1/2, or we can say T times 1.5 meters. And then I said this is a positive torque, and we know that. Just be sure about that. If this were to pull strong enough to make rotations start to happen, an upward pull out here at the end would make the beam rotate that way, counterclockwise. And if a torque makes counterclockwise rotations happen, it's a positive torque. So it had to be a positive torque in order to cancel out this negative torque, because we knew the net torque was 0. So we just do the algebra here. 588 Newton meters divided by 1.5 meters is the tension in newtons, and that'll come out to 392 newtons. Every other problem involving equilibrium works just about the same way. We find out what the forces are, we figure out what the torque is from each force, and then we write down the way those torques combine to give you the net torque. That's what I did right here, and then we've got an equation that we can solve for whatever it is we're looking for. So let's look at another example. I'm standing on a board, and there's 2 blocks here at the ends to support the board, and the board is again 3 meters long, and I'm standing over here 2 meters from the left end, 1 meter from the right end. There I am. And let's say the board, in this case, has some mass. Mass of the board, let's see, what mass of the board, let's say, is just 10 kilograms. And my mass of me, 80 kilograms. And that's all the information you need in order to figure out how strong the support forces are at the left end and the right end. So let's start the same way. What are the forces? Which way do those forces point? Where are those forces acting? So one force is the support force on the left. It's a normal force. The top of this block is a horizontal surface which is pushing vertically on the board. So we'll call that normal force from the left block. And then similarly, there's a normal force from the right block. And then 2 more forces. There's the weight of the beam, which is pulling on the center of gravity, which will be right in the middle. We're assuming that the mass is evenly distributed along the whole length of the board, so the center of gravity is right in the middle. So there's the weight of the board, which is just mass of the board times g. And then there's one more force from me pushing down on the board. That's a normal force. Don't call it weight. It's closely related to my weight, but it is not a weight force. It is a normal force. Normal force from me on the board. The bottoms of my shoes are horizontal surfaces, and they are pushing vertically on the board. That's where that normal force from me on the board comes from. But it turns out that this normal force happens to be the same magnitude as my weight. It's not a weight force, but it does have the same magnitude as my weight. Just to think about that for a minute. Here I am I'm in equilibrium. I'm just sitting still. My acceleration is 0, so the net force on me is 0. Because the two forces on me are my weight, which is mass of me times g, and then the board is applying an upward normal force supporting me, a normal force from the board on me. Normal from board on me. And since I'm in equilibrium, I have 0 acceleration and the net force is 0. Net force on me is 0, which means those two forces have to be the same strength so that they can cancel each other out. Normal force from the board on me equals my weight. But, now think Newton's third law. If there's a force from the board pushing up on me, there's an equal and opposite Newton's third law pair force from me pushing down on the board. And the force with which the board pushes up on me is just as strong, equally strong, as the force with which I push down on the board. So these two forces are just equal to the normal force from me on the board. Those two forces are equal because they're a third law pair. These two forces are equal because of Newton's second law and the fact that I'm in equilibrium. My net force is 0. So now we know that we're able to figure out this number because this force just happens to be equal to my weight. So those are the 4 forces. Now let's we want to see how the torques add up to give the net torque. We also often want to, it's often necessary to write down an expression that shows how the forces combine to give us the net force. So let's do that. The net force, which is 0, is just all the upward force, normal force from the left block plus normal force from the right block, minus all the downward force, which is the weight of the board, minus the normal force from me on the board, which is equal to my weight. Mass of me times g. And of course, that's all going to add up to 0. I'm in equilibrium, so the net force on me is 0. Now let me redraw the forces again. Mass of the board times g, the weight of the board, and then the normal force from me on the board, but the strength of that is equal to my weight, which is my mass times g. Okay, now I want to solve for both of those normal forces. I can make it easy on myself by choosing the reference point either at one end or the other, because again, that'll put one force right at the reference point, so that force will produce 0 torque, so that unknown force will not appear in the torque equation. It'll make the algebra easier. So let's say I put the reference point right here at the left. Now, what do the torques look like? Torque due to the left side normal force is of course 0, because the displacement vector, which takes us from the reference point to the point where the force is applied, is 0 in this case. So that 0 is a factor in calculating this number, so this number just comes out to 0. Now, torque due to the mass of the board, or torque due to the weight of the board, the first factor is the magnitude of the force, which is the magnitude of the weight. That weight was a mass of 10 kilograms times g, 9.8 meters per second. So that'll be just 98 newtons. Next factor is the magnitude of the displacement. Displacement takes you from the reference point to the point where the force is acting. This weight force pulls on the center of gravity, which is right in the middle of the board. So that's the whole board is 3 meters long, so halfway along the board is 1.5 meters. And then the last factor is sine of the angle between displacement direction and force direction. Well, the displacement direction was a displacement from here to here. So again, the displacement is straight to the right, and the force is straight down. So the angle between displacement and force is 90 degrees. So that sine factor in the torque equation is sine of 90 degrees, which is 1, again. And is that torque positive or negative? It's going to be negative because if this pull were strong enough to make the board rotate about this reference point, it would rotate clockwise. And a torque that makes a clockwise rotation happen we call a negative torque. Next, the torque from the force that comes from me, which is equal to that force is equal to my weight, mass of me times g. So the first part in the torque equation is the magnitude of the force, which is my weight, which is 80 kilograms times g, 9.8 meters per second. And then the next factor is the size of the displacement vector. The displacement takes us from the reference point to where this force is acting. I'm 2/3 of the way across the board. The board is 3 meters long. I'm 2 meters away from the right end. So the displacement has a magnitude of 2 meters. And then, same as in the previous example, the sine of the angle between displacement direction and force direction is 90 degrees again. Sine of 90 degrees again is 1. And this kind of force, a pull down here, would produce the same kind of rotation clockwise as this pull. So both those torques produce clockwise rotations, so they're both negative. Finally, the last torque is the torque from the last force. I'll have to write that up here. Torque from the right-hand support force. And that force is just torque. Again, same idea. Magnitude of the force, but in this case, we don't know that force. That's something that we're trying to figure out. So we don't put a number there, it's just an algebraic variable. The magnitude of the force is NL. Whatever that is, we'll figure out in a minute. Then the next factor is the size of the displacement vector, which takes us from the reference point right to there, takes us across the full 3 meters of the board. So the magnitude of that displacement vector is 3 meters. And the sine of the angle is again the sine of 90 degrees because again, the displacement vector is horizontal and the force is vertical. So the angle between displacement vector and displacement direction and force direction is 90 degrees. Sine of 90 degrees is 1. This torque, unlike these two, would have to be a positive torque. And it's a positive torque because if this upward pull here at the end could make the board rotate, pulling up, so the board would be rotating this way. It would be rotating counterclockwise, and a torque that makes counterclockwise rotations happen is a positive torque. So there's the 4 torques, and now we write down the way the torques add up to give us the net torque. So the net torque, which is going to be 0, is just a sum of 4 torques. This torque, which is 0 itself, plus this torque minus 10 times 9.8, or 10 kilograms times 9.8 meters per second. So that's 98 newtons, weight of the board, times 1.5 meters. And then the next term is minus 80 times 9.8, or 784 newtons. Times 9.8 is 784 kilograms, times meters per second is newtons, times the magnitude of the displacement, which was 2 meters. And then the last torque, that one, which is just magnitude of the force that we're trying to figure out, times magnitude of the displacement vector. Okay, so all that has to add up to 0. And what does that algebra look like? So 98 newtons times 1.5 meters is minus 147 Newton meters. And then the next one, 784 newtons times 2 meters, is minus 1,568 Newton meters. And then the last torque, which is NL newtons times 3 meters. So this torque must be just as big as the sum of these two torques. All the positive torque has to cancel out all the negative torque to keep the net torque equal to 0. So this plus this has to equal this, or 1,715 Newton meters. That's this, and this must be equal to NL times 3 meters. And then when you divide both sides of that equation by 3 meters to get the strength. Oh, sorry, that's the normal force on the right. The normal force on the left had a torque of 0. So let's fix that. Right. Normal force at the right end of the board. But anyway, the algebra comes out the same. This divided by 3 meters gives us the strength of that normal force, which will be normal force from the right block on the board is 570 newtons. Okay, now, knowing that number, now we can figure out the strength of the force at the other end, the strength of the normal force at the left end, because we still have this equation. We know those two numbers, we can figure out the weight, And now we know this number as well. So net force is 0 because we're in equilibrium, and that's equal to still unknown, but not for long, normal force at the left end plus normal force at the right end. We just found that to be 570. Minus the weight of the board. And remember, the weight of the board was 10 kilograms times G's, 10 kilograms times 9.8, that's 98 newtons. Minus my weight, which was 80 kilograms times 9.8 meters per second, and that came out to 784. And that all has to add up to 0. And when you do the arithmetic there to figure out what NL is, you'll find that it comes out to about 312 newtons, or we'll round it off to just 310 newtons. Okay, and then when we get to class, you'll see that every other equilibrium problem is essentially the same as this. We go through exactly the same steps. It still takes a little bit of getting used to. Correctly writing down the torques that each force produces can be confusing, but it gets a lot less confusing with a little bit of practice.